All right, we are live.
Right, great. So today I'm going to talk about Bousfield localization and Bousfield equivalence. It's mainly going to be a survey, so I'm not going to provide a lot of proofs. Some of the proofs are written up in the Orange Book and or in the paper, so if you're interested, you can check them out. I think I'm going to prove like two things. So first, I'm going to start off with some basic definitions of, for example, E acyclicity, E equivalence, and E local. So a spectrum X is E acyclic if the E homology of X is 0. And then a map F from a spectrum X to Y is E equivalence if it induces isomorphism on E homology. And then finally, a spectrum Y is E local if all the maps from, if we have a E acyclic spectrum X and all the maps from X to Y are homotopic to the null map. So that is the definition of E local. And we, based on the name localization, we have a way to localize any spectrum to make it E local. So we have a E localization functor L sub E that takes it's a covariant functor, and it takes a spectrum X to a E local spectrum LE of X with a natural transformation eta of X from the identity of X to LE. And there are two properties of this. So first of all, actually, before that. So first of all, eta of X is the E equivalence. And second of all, for any equivalence, F from X to Y, you actually have an extension of F. So you actually have a map from Y to LE of X such that we have this commutative diagram. So if we have, this is F eta, you actually have a map G from Y to LE of X such that this thing commutes. So in other words, eta of X is the terminal E equivalence that you can get from X, which is shown by this commutative diagram.
Just to clarify, on top you wrote LE from X to LEX. LE is not the function from X to its localization, right? It's the function that takes X to its localization.
Yeah, LE is the function that takes X to the localization. So eta of X is the natural transformation evaluated on X. So
Right.
it's from X to LE of X.
Yeah.
That is an equivalence. So it's like the farthest equivalence, I guess that means, because it's terminal from X that you can get. And then, I mean, you can get to a E local spectrum. And then there are some properties of E locality. So first of all, And my handwriting is kind of bad on iPad, but I do have a set of notes that I'm gonna upload after the talk. So it's typed up, so it should be clear. And then, first of all, E of locality is preserved by, quote, I think it's inverse limit. Non-necessary direct limit, I think there are a couple of examples in the paper that has something to do with Morse spectrum. So if you want to check that out, it's in the paper by Ravenel. And second of all is, so in a co-fiber sequence, W to X to Y, if two items in the co-fiber sequence are E-local, so is the third. So that's kind of like a 2 out of 3 property. Also, it's preserved by wedge sum. Which means if X wedge Y, not smash, is E-local, so is X and Y. Okay. And then I'm gonna talk about some properties of LE. So first of all, LE is unique, as we'll expect. Second of all, LE is idempotent. I don't know how to spell this. Idempotent. Which means that if you apply LE twice, you actually just get LE. Third of all, this is another kind of categorical characterization of LE of X. So if you have any map F X to Y that is such that Y is E-local, the map F has to factor through 8 of I think. Actually, have to factor through 8 of us. So if we have this map F and Y is E-local, this map actually have to factor through LE of X, and we get something like this. So I guess that tells us that the functor, LEX is the initial object that is E-local, and X maps to that object. Let me see. Okay. And then I'm going to give a proposition. This is just straight from the definition. If E and F are spectrum, then if E of X implies E of X is 0, implies F of X is 0, then a spectrum that is F local is also E local. Okay. So if E of X is 0 is equivalent to F of X is 0, then the two functors LE and LF are actually the same. Okay. And Bousfield proved this theorem that actually states the existence of Bousfield localization. So for any homology theory, E in any spectrum X, the localization LE of X exists and is functorial in X. Okay. So as I mentioned that LE, sorry, as I mentioned, any inverse limit preserves E locality, but it's not necessarily true for direct limit. And LE does not necessarily have to commute with inverse limit. There are some examples in Ravenel's paper about this. But later I'm gonna introduce a nice kind of spectrum that you actually do get some of those properties of with inverse limit and direct limit, but I'll talk about that a little bit later.
Wait, I'm a little confused. You said that it preserves inverse limits, but also it doesn't preserve inverse limits?
Sorry, no. I said that E locality is preserved with inverse limit, but LE does not have to commute with inverse limit.
It's the difference between the category of local spectra versus the functor that localizes.
Yeah. And
right.
And direct limit does not have to preserve E locality. That's kind of two different things.
Right. Right, okay, because LE is the left adjoint.
Yeah, okay. That's not have to preserve that.
Can you go back to the properties just a little bit up?
Yeah.
So yeah, these how far are these properties from the properties you need to be a thick subcategory?
I think thick subcategory you have to be preserved. So like that has to be closed under cofibration and retract, right? And I don't really remember the other ones, but I think those two are like the two most important ones. For thick subcategory. Let me just quickly Google since we're
they're pretty close, but not quite the same. This is what's called a localizing subcategory. They're characterized by as being the categories you get from Bousfield localization, and basically the difference between localizing subcategories and thick subcategories is like the difference between TN locality and KN locality. So like if you want to look at the Balmer spectrum, the ordinary thing you do would be to look at thick subcategories of the small stuff, but you could also look at localizing subcategories of the big stuff.
Yeah, I do see that for a thick subcategory, you have to be close on a direct summon. So it's what this this class of spectrum also have. But I think so. The one you just said that the thick subcategory is bigger, it has more requirements, right? Or it has less.
Yeah, there are fewer thick subcategories.
Okay, so it has more restrictions.
Yeah, I was just wondering what's missing because you also have this coat fiber sequence condition too. But
yeah, I mean the cofiber sequence condition does imply that it is closed under direct sums or aka wedge products, because that's the 2 out of 3 condition. But I believe localizing is it's either slightly weaker or slightly stronger, but it comes down to whether you care about finite things or infinite things.
Okay, great. So we just mentioned that this thing has to exist. And yeah, there are some counter examples of when this thing is not behaving very well. And then I'm going to give one example that's also on Ravenel's book that tells you that localization, like the spectrum that you get after localization could be contractible, but the spectrum itself is not necessarily contractible. So so let me write this. Does not direct limit does not preserve locality. And then inverse limit does not commute with LE. So two different things. Okay. And then I'll give this example. So if E is just the ordinary cohomology, let me denote ordinary homology. And then X is a spectrum that is finite. And it also has a property such that Kn of X is not zero. So Kn is the nth Morava K theory. And then X also has a Vn self map.
Wait, is that supposed to be that it is zero or it isn't zero?
I think it isn't zero, you're right. So Vn self map. So just to remind you guys what a Vn self map is, so it induces isomorphism on Kn homology, and so that's the n in Vn. And then when M is not n, then the F is nilpotent, but not necessarily a zero. It's not necessarily zero. Let me just write that down. So just a reminder, a Vn self map F. So Kn of F is isomorphism, and a Kn of F and not n is nilpotent. So that's the definition of Vn self map, and X has to have a Vn self map. So that's the properties of X. So we can define the telescope X hat to be just the limit of this direct limit of the system when you iterate F. So you go to some desuspension of X, and then you just keep going. And then we know that if we localize the telescope with respect to the ordinary cohomology H, where I said E, okay, let me just say E. This is going to be contractible because we just said that Km is nilpotent, and we also know that K infinity is, I think, the ordinary cohomology, ordinary homology with coefficient Fp, right? If you choose a prime P. So then we know that because E of this is going to be zero. And then, so the ordinary cohomology of the telescope is just going to be zero. On the other hand, we know that the telescope itself is not contractible. It's not contractible because F induces an isomorphism on Kn of X, on Kn, and we know that Kn of X is not zero, which is equal to the Kn of the telescope, because all you do is just reiterating F. So this is not 0. Then we got this telescope whose localization with respect to the ordinary cohomology is contractible, but it is not contractible itself. So that's, I guess, kind of the strange behavior of localization function. Just want to take this example. And
Oh, I should add, I double checked. This is in I think the intro of Barthel and Beaudry's chapter, but they define a localizing subcategory to be a thick subcategory which is closed under infinite direct sum, as well as finite sum.
okay, great. Thank you for mentioning that. And now let's but the ring spectrum actually behaves relatively well with E locality. And here is a proposition. So if E is a ring spectrum, then any E module spectrum, for example, E smash any spectrum X is E local. So this is not necessarily true if E is not a ring spectrum, but it is true for ring spectrum. So I'm gonna quickly say the proof of this thing. So we want to show that E smash any spectrum. I'm just gonna show the E smash X part. So for any, we want to show that for any spectrum W that is AE cyclic, which means that E smash W is 0. We want to show that the homotopy, all the maps from W to E smash X are homotopic to 0. So the homotopic set of homotopic map is just 0. Since E is a ring spectrum, we have this multiplication map. I'll call it mu from E to E times E to E. And then we can build this commutative diagram. So the top layer is from W to E smash X, we'll call that F. We want to show that F is no homotopic. And then we also have a map from W to E smash W. That's just gonna be mu eta, eta. So we can add like a sphere spectrum here. And then here we have E smash X. So this will just be E smash F. And this will be eta smash X. And then because we have this multiplication map mu, we have this, we can be mu smash X. And then here is another map that's just identity smash X. So we know that.
What is eta here?
I think eta is just eta is the localization. It's the natural transformation for localization. I think it should be eta of E, right?
Are we assuming here that E is smashing, or that E localization is smashing?
I don't think we assume smashing here. I haven't talked about smashing yet.
So why is it that the E localization of the sphere spectrum is E?
Actually,
I think it's just the unit. I don't think this is the localization.
Okay.
So so eta is a unit, right?
Is the unit of E as a ring.
I see.
So in order to be a ring spectrum, you need to have a map from S to E.
Oh yeah, sorry. Yeah, you're right.
It's part of the structure.
So
My question then is, what is the map from E to E smash E that is
So you can just
being
smash
smashed
with the
into
sphere
X?
spectrum on top.
I
Yeah.
see.
yeah, here you can smash.
Yeah,
So,
just think of it in terms of the square it needs to commute. So there's one thing it should be.
okay, so yeah, sorry. Eta is not, just for the record, eta is not localization because the book used different notation. Should have checked that. Eta is the unit from the sphere spectrum to E. Okay, now we're good. And then since we know that E smash W is contractible, because that's the definition of W being E acyclic, we can just deduce that F is known because commutativity. So that's what we want. So note that there's something that this thing does not imply. So the localization functor for especially a for a spectrum that's not connected is quite it's quite complicated. So let me write this down. So note, even if E smash X is E local, LE of X does not necessarily have to be E smash X, because we said that is the initial, initial E local, the localization is the initial E local spectrum that X mapped to. So it might be something in between that's closer to X than E smash X. Okay. And then there is this definition of, I don't think this thing is actually used later, but let me just introduce it for now. So there is this E Nilpotence spectra. So for a ring spectrum, E, there is the class of, we can form the class of E nilpotent spectra that is the smallest class that satisfy the following requirements. So first of all, E itself has to be nilpotent. And second of all, if N is E nilpotent, so is N smash any other spectrum X. Right. And then it has to preserve co-fiber. So like any co-fiber between E nilpotent spectrum has to also be E nilpotent. And the last one, it also has to preserve retract. I was actually wondering, because you guys just mentioned the localization class. Is the nilpotent class the same thing? I don't know if the nilpotent class and the localization class is the same thing, because
Not quite. It looks like this is the thick. This is the thick subcategory, and also it's closed under. It absorbs smashing from the right, so it's a right. We would say it's a right tensor ideal. It's a thick tensor ideal, I guess.
So I guess
The
this
thick.
even
When I
bigger.
say tensor ideal, I mean just with like it's an ideal with respect to the smash product. Like if you smash something with something that's in this subcategory, then you'll remain in the subcategory. So it's like the thick tensor ideal generated by E.
Okay, and there's a proposition stating that E nilpotent spectra are E local. I don't I'm not going to prove this. It's just something that he brings up in the book. Right. Now we're going to talk finally about Bousfield equivalence. So for spectrum E, let E, this bracket E denotes the equivalence class, Bousfield equivalence class of E. And the equivalence relation is that E is equivalent to F if E the E homology of X is 0 if and only if the F homology is 0. So this means that E smash X is 0 if and only if F smash X is 0. Okay, sometimes I'm going to use the word annihilating, which just means that smashing. So like if E is annihilating something, I mean that E smash something is 0. Okay. I mean, that's not 0, but it's just contractible. Let's make it more precise. Contractible. Okay. And then equivalently, E is equivalent to F if and only if a E equivalence is F equivalence. And an F equivalence is E equivalence. Follow me. Write it like this. Okay. And so we call the bracket E the Bousfield class of E. And then there's a order, I guess partial order in this thing. So if F is bigger or equal to E, if every F acyclic spectrum is also E acyclic. And then there is if it's strictly bigger, that means that it's bigger or equal than, but it's not equal. I'm not gonna write that. So A class E has a complement we'll denote that with a superscript C. If there are two, so if E smash its complement is the Bousfield class of a point, which is the smallest Bousfield class. We'll talk about that. Because if a point is smash anything, you want it to be like a point. The thing could be like anything. So it's like the smallest. Because I will actually think that will be the biggest, but based on the definition that of bigger or equal to is actually the smallest. And E, if we wedge E and E complement, that has to be the sphere, the Bousfield class of the sphere spectrum. Because the sphere spectrum smash anything is the thing itself. So if you want it to be 0, the thing that you smash, if you want it to be contractible, the thing that you smash has to be also contractible. So that means that the sphere spectrum is actually the Bousfield class of the sphere spectrum is actually the largest Bousfield class, although I will argue is the smallest, but let it be. And there are some simple properties of Bousfield class. So at first it commutes with smash and wedge. So and then we also have a couple of distribution laws. So this one, sorry, that's not, yeah, I mean, you're right. E smash F. And then we can distribute the smash product. So it'll be E smash G wedge F smash G. And then we also have this for wedge. So E smash F wedge G is E wedge G smash E wedge F sorry. F wedge G. Okay. And then there are some simple examples that you can have, as I just mentioned. The Bousfield class of S is the biggest. It's bigger or equal to any Bousfield class, which is bigger or equal to the Bousfield class of a point. E is just a spectrum. And then we have this is just E, which falls from the properties above. And wedge E. The Bousfield class of X wedge, the Bousfield class of E for any spectrum E is the Bousfield class of X. This is just pretty direct, pretty straightforward. And then a point smash E is just a point, because a point smash anything is a point. And then a point wedge E is E itself. Okay. And there is an important proposition that I'm gonna mention because it has something to do with the construction of the chromatic tower. So the localization LE is the same thing with the localization of LF if the Bousfield class of E and F are the same. So this connects the localization functor with the Bousfield class that we just introduced. And also, if the Bousfield class of E is smaller or equal to the Bousfield class of F, then if we apply LF and then apply LE, you just get LE. So you can think of this as the localization of E is a little bit stronger than the localization of F. Moreover, there is a natural transformation from LF to LE. Okay. And
Well,
then
I have a question about the complement. So we have this definition in terms of the lattice. I'm curious if the complement can be described as the acyclization. Like, if I have a spectrum E, I can look at the acyclic part of some X, with the E acyclic part. Is that the same as the E complement localization, or are they related?
I've never heard of the acyclization. Can you maybe say that again?
So if you have E and you have some spectrum X, you get a fiber sequence, which is X maps to LEX, but then you also have the fiber. So LE is the localization, but then the fiber is the acyclization, which is like, you know, if LE is the smallest E local thing, then the fiber is the biggest E acyclic thing. And I'm curious if, you know, if E has a complement, is that equal to the acyclization?
Yeah, that might be true. I've never looked into that. Maybe let me think more about it after the talk, and then I'll let you know. But the acyclization definitely makes sense. But I think it makes sense, but I'm not sure. Okay. Let me move on. So I'm gonna just, I don't even know. I'm gonna briefly mention, maybe let me skip this part because we only have 20 minutes left. I said that I'm gonna tell you guys about a nice class of spectrum. It's called smashing, as Sora mentioned a little bit before. So the spectrum E is called smashing. If the Bousfield class of E is the same as the Bousfield class of the sphere spectrum localized at E. And if a spectrum is smashing, it actually has some good properties. For example, I don't know how to prove this, but the paper talks about it. So this is E. I think eta here is the localization, is the natural transformation from identity to localization. If it's eta of S, I guess, is evaluated on the sphere spectrum. So this thing is an E localization. Moreover, we have that the rack limit. Now, also the rack limit of E local spectrum is E local. So that's something that we don't necessarily have if E is just any random spectrum. And also the third one we have is that LE commutes with the rack limit. Right. I think I said that LE does not have to commute with inverse limit, but if you're smashing, LE now commutes with direct limit. Okay.
Shouldn't LE always preserve direct limits since it's a left adjoint?
Let's try to see this real quick because I think it says direct limit in the paper, but I might be wrong. Yeah, here it actually said that it commutes with direct limit. Yeah, I think you're right because it's a left adjoint. So it should commute with direct limit anyways, but it's listed as a property of smashing.
All right.
I guess there's something special about LE that. And then I don't know if I want to talk about this, but let me just mention the class invariance theorem real quick. It is a very pleasant, as Ravenel says, is a very pleasant consequence of the thick subcategory theorem. So if X and Y are both CW comp P local finite CW complex, and X is of type M, Y is of type N. So we get that the Bousfield class of X and Y are equal if and only if M equals N. We get that the Bousfield class of X is smaller than the Bousfield class of Y, and that only if M is bigger than N. I think you can use some other properties of Bousfield class together with the subcategory theorem to prove it. I have to prove since I don't have time. I'm not gonna say it. Okay.
Yeah, it sounds like.
Sorry. Go ahead.
Sorry, it sounds like just knowing that localizing subcategories are thick subcategories already, and the thick subcategory theorem already imply this. Is that it?
Yeah. So like the idea is that we can build a thick subcategory, the smallest one containing X and containing Y. And then we can actually show that C of X, which is the smallest thick subcategory containing X, actually equals the F of F sub M, which is I think the type M finite CW complex, and then you can show that C of Y equals F of N, and then that shows you that C of X is C of Y if M equals N, and that tells you that the Bousfield classes are the same. So yeah. Okay. And I just want to tell you guys a fact that so let me introduce the Braun commonness duality. So let Y be a spectrum of finite homotopy groups. We can there's the spectrum C of Y, which is the Braun commonness duality, a dual of Y, and that satisfies, because it's called the dual, we will expect that if we apply C twice, we get Y back. Second of all, the more important one is that, so the homotopic class of maps from X to C of Y, that. So the negative I level is isomorphic to hom from pi I of X smash Y with 2R, which is a real number, mod Z. So if we take X to be the Fear spectrum, we get that pi negative I of Y is isomorphic to hom of pi I of Y to R mod Z. Okay. And Ravenel gives an example, which I don't know why. He says that the Braun commonness dual of the Morse spectrum is just the mod P Morse spectrum is just itself. Okay. And so it follows that if homotopic set of map from X to E to C of Y is 0, then it follows that X smash Y is contractible. So if homotopic set of map from X to Y is 0, then it follows that X to smash C of Y is contractible. And then we can take X to be MU, and we can take Y to be a finite spectrum with trivial rational homology, and then you can do some tricks with the atom spectral sequence, and you can actually show that the homotopic set of maps from X to Y is just 0. So that means that the MU homology of CY, the dual, is 0. Then we know that there exists this non-contractible spectrum C of Y, but with trivial MU homology. That means that, because we know that the sphere spectrum is, the Bousfield class of the sphere spectrum is bigger or equal to any of the Bousfield class, but we actually produce this spectrum such that is annihilated by MU, but it's not contractible itself. So we know that the Bousfield class of the sphere spectrum is strictly bigger than the Bousfield class of MU. So this is a takeaway from, this is why we introduced Braun commonness duality. I'm just going to mention this, but especially there is not only just one of such spectrum that we can find. There is actually a sequence called X of XN, with X1 is SO and X infinity is MU. And we also get that the Bousfield class of Xn is bigger than the Bousfield class of Xn plus 1. So it gets bigger and bigger when you go from S to Mu. And I think this is actually introduced in the proof of periodicity theorem, and that you can construct S using the homotopy, using the bar periodicity. I'm not going to mention that, but basically we have that the ordinary cohomology of Xn is Z adjoined with a bunch of generators B1 to Bn, and the generator is actually mapped to the generator, if you remember, was the ordinary homology of Mu. The generators B1 to Bn actually map to the generator of H of Mu with the same name. So there's this sort of correspondence between Xn and Mu with respect to the ordinary homology. Okay. And let me see if I want to.
Do we know that these are strict inequalities?
I don't think they have to be. It doesn't say that it's strict. So
I mean, it would have to be if Xn has N generators over Z, which are distinguished. Right?
Yeah.
Not necessarily. I mean, like, it doesn't tell you that localization is necessarily different. I mean, maybe it's plausible.
Right. I guess it may not be strict in terms of the Bousfield classes, but it is at least strict in terms of the spectra.
Yeah, but like KO and KU have the same Bousfield class, so.
Right.
Okay, so it might not. I guess it might not be strict then. And then there is this localization theorem that I'm just gonna state without saying anything about it. So let Ln denote N of X denote the localization at En of X. So En is the Morava E theory. We have BP smash Ln of Y equals Y actually smash Ln of BP. Is that right? Yeah, that's right. I think this is going to be proved in the next chapter. I just want to mention it so that when you guys see it, it's yeah, it's here. So let me just quickly talk about the chromatic tower, which is pretty essential to chromatic homotopy theory. So the chromatic tower for a p-local spectrum X, so X has to be p-local, is a inverse system that you get from X1. I will talk about why this map exists in a moment, but let me just write it here. All right. We know for a fact that E in the Bousfield class is the wedge from I equals 0 to N of the Bousfield class of Ki. So we know that this tells us that the E in Bousfield class is smaller than the Bousfield class of E n minus 1, right? And then based on something I talk about, I don't know where it is, but let me try to find it. Basically, something I talk about says that if the Bousfield class is smaller, then you actually get a natural transformation from the other way around. So we get a natural transformation from L n minus 1 to Ln. So that's why we have this system of maps. And then I'm gonna mention, I guess I feel obligated to mention the telescope conjecture. So if for X is p local, it is a p local finite CW spectrum, CW complex with type N. and then also with a VN self map. Actually, it doesn't even have to be a V. I think it has to be a VN self map. I'm sorry, VN self map. F. We can form the telescope, and we also know that because Kn of F is isomorphism, and because it's type N, so Ki of F is just 0 for I is smaller than N. We know that, so En of F based on this relation is an equivalence isomorphism. Equivalence I wrote it here. So that x to ln of x, it has to factor through the telescope. So we have this map from the telescope to ln of x, we just call that lambda. Ravenel stated that lambda is a BP equivalence by the localization theorem, and I guess the telescope conjecture states that lambda is actually a isomorphism, right? But I think Miller and Mahal proves that telescope conjecture is true for n equals to 1 or 0. I don't remember, but we don't know anything. We know something, but we don't know completely if it's true for like n and other, like for other prime p.
Yeah, it's true at height 0, and it's true at height 1 at the prime 2.
Yes,
I believe.
I don't know anything about. I think it says that Ravenel, someone was able to disprove something. Let me just check real quick for a higher height, but I'm not exactly sure what height is that. So
I think I'm gonna have to head out.
Okay. Yeah.
Wait, let's thank our speaker.
All right. Sorry for the messy notes, but I'm gonna upload. I guess I would just email you and the lecture notes that I typed up, and then you can upload that to the website.
Yeah. Perfect. Thanks. All right. See you all next week.
I should mention